Looking at some of the groups in particular, let's start with the noble gases. So usually when we think of noble gases, we think of inert gases that don't react to form any compounds. That's mostly true, but you do have to watch out for xenon tetrafluoride. So XeF4 is one of the compounds that is formed by a noble gas. Another trend that you need to know is the melting point specifically of the alkali metals and the halogens. So they're actually opposite, so it's sort of important to remember which one is which. When we're looking at the melting point of alkali metals, as we go down a group, the melting point decreases, so you need less energy to melt the alkali metals, whereas as you go down the halogen group, my melting point increases, and we're going to look a little bit at why in a second. As we go across the periodic table, again, it's not very straightforward. Metals tend to have an increasing melting point until we reach group 14. That's the highest, and then starting at group 15, we have a very low melting point that increases. So alkali melting point has to do with atomic radius. So the forces that are holding these metals together are known as metallic bonding, and it has to do with the idea that we have positively charged nucleus that are electrostatically attracted to electrons around them. The larger the atomic radius, the slower the attraction is between the nucleus and the electrons. On the other hand, halogens are a little bit different. They don't use metallic bonding to stick together. They have another intermolecular force that basically increases with mass. In topic 4, we're going to look at something called London dispersion forces, but the basic idea is the larger the molecule, the heavier the molecule, the more attraction it has for other molecules of a similar kind. Okay, we can see that if we go down a group. So fluorine and chlorine are both gas, bromine is a liquid, and iodine is a solid. So you can see how going down the group, we slowly get to have stronger attractions between our halogens. As we go across the period, we have metallic bonding, which is quite strong. It's usually very rare to find a metal that can be easily melted. And then as we continue along getting into the nonmetals, we have giant covalent bonding, things like diamond and sand, which have very high melting points. And then at the very end, we have covalent bonding, which is not very strong intermolecular forces. Again, we're going to look at this in topic 4, the next topic, but you do sort of need to know the general shape of this trend. In addition, let's take a closer look at group 1 and 2. So group 1 and 2, as we saw in our previous video, have low ionization energies, meaning they don't require that much energy to remove the outermost electron, so they're usually electron donors. Whereas group 17, the halogens, have very high electron affinity, meaning that they usually accept electrons. What that looks like then, if we have a reaction between these two groups, is something quite explosive. So for example, let's take sodium and react it with chlorine, and we get table salt. This releases quite a lot of energy. Again, chlorine accepts electrons and sodium donates electrons. So chlorine becomes -1 charged and sodium becomes +1 charged. The other type of group-specific reactions that you need to know are something called displacement reactions, specifically for the halogens. So in your previous chemistry classes, you probably learned displacement reactions is where one element comes in to take the place of another that's in a compound. In this particular reaction type, we're dealing only with halogens. So let's just remember where they're placed. So we have fluorine at the top, then chlorine, then bromine, then iodine. And if we're thinking about electron affinity, what's going on is fluorine has the highest and iodine has the lowest. That gives us a sort of way to predict what kind of halogen displacement reactions will happen. So take a look at what I'm drawing right now. So we have iodine, bromine, chlorine, and fluorine. And we're going from the poorest electron grabber, so they're the worst at grabbing electrons, to the best electron grabber. So it has the greatest electron affinity or the greatest electronegativity. On the other hand, the ions of the respective halogens are therefore iodine is the best electron donor. It's the weakest at grabbing electrons, but the best at letting its electrons go. And fluorine is therefore the worst electron donor. What that means is sometimes displacement reactions between halogens may not work. Let me show you an example. So here we have fluorine gas, and it's reacting with sodium bromide. And just a reminder, in this ionic compound, sodium has a charge of plus, bromine has a charge of minus. Let's figure out what's going on based on this table. So I circled fluorine and I circled bromine. And what's going to happen is fluorine's going to try to go in and grab bromine's electrons. It is able to do so because it is a better electron grabber. It has a higher electronegativity, and so it's able to go in there and form F minus. Let's take a look at another example. So here we have iodine reacting with sodium fluoride. Again, I circled it on our scale. Iodine is the worst electron grabber, so it's not going to be able to grab the electrons from fluorine. And fluorine is the worst electron donor, so that reaction will not happen. There will be no reaction. So again, fluorine can displace bromine by stealing its electrons because it has a higher, more negative electron affinity and a higher electronegativity. The last trend that the IB wants you to know about is this idea of metallic character. So we can characterize how metallic an element is. And that means how good it is at giving away its electrons, how malleable it is, and how ductile it is. So how similar to being a metal is an element. And this trend basically increases as we go up a group and increases as we go from right to left. So increases up a group and increases right to left.